In this video, we will talk about what concavity is. So let's begin with the definition. The first part of it says, if the graph of our function f lies above all of its tangents. So what I mean by tangents is its tangent lines, all of its tangent lines on an interval I, we say that our function f is concave upward on that interval I. Alrighty, so sometimes I'll abbreviate concave upward by writing CU. Okay, so there's a similar definition for a concave downward. So I'm just going to put a bunch of quotes here. A bunch of these words are going to be the same. The quotes just mean a bunch of words are the same. And then the difference is if the graph of f lies below. And then it continues in the same way. All of its tangents on an interval I, we say that f is concave downward. F is concave downward. Or I'll abbreviate that as CD for concave downward on our interval I. So one more time, the quotes just mean that I'm just writing all the words the same, except for the words that I've actually written in, like below and I and concave downward, just to save some time. All right, so let's draw some pictures to show what these look like. All right, so let me draw two pictures. So I'll draw two pairs of axes here. So first I'm going to draw this sort of parabola shape. And with this parabola shape, I'm going to draw a couple of tangent lines. So at this point, if I draw a tangent line, that would look something like this. At this point, if I draw a tangent line, that would look something like that. So our graph of f here lies above these tangent lines. And I think it's easy to see that even if I were to draw a different tangent line at a different point, the graph would still lie above that tangent line. So by definition, this is concave up, or CU. Okay, let me draw something that's concave down. Okay, so I'm going to draw this shape. Now let's draw a couple of tangents. So at this point, if I draw a tangent line, that looks like that. If I draw a tangent line at this point, that looks something like this. So here, the graph of our function lies below. The graph of our function lies below all of its tangents. That makes this one concave down. Okay, so on a more kind of basic graphical level, a concave up graph has this sort of upwards U curve, like upwards U shape, and a concave down graph will have sort of a downwards U shape. All right, let's do an example where we practice this more. Okay, so this is example 3, and I have this function and its graph drawn here. I definitely pause the video or so for a minute just to copy this down. But what I want to do is identify on each of these intervals that sort of split off at A, B, C, D, and E, is my graph concave up or is it concave down? Okay, so on this first interval, to the left of A, my graph has this sort of downwards U shape, so it's going to be concave down. I'm just going to write concave down, or I could write CD for concave down on this interval. And then from A to B, it has this upwards U shape, so that is concave up. So concave up, I'll write CU for concave up. Okay, and then from B to C, it has this downwards U shape, so that's concave down. I'll write CD over there. And then from the points C to D, it's upwards U shapes, that is concave up. From D to E, it's still upwards U shapes, that is still concave up. And then from E onwards, it has a downwards U shape, so that is concave down. Concave down over here. All right, so there's some terminology that we can use to talk about points on the graph where it switches concavity, like from concave down to concave up, like it does at A, or from concave up to down, like it does at B. And that is called an inflection point. So our definition will say that a point P on the curve y equals f of x is called an inflection point if f is, so our function needs to be continuous there. If it's not continuous there, it doesn't even matter. It's not going to be an inflection point. It's got to be continuous there at the start, and f changes concavity. F has to change concavity there. So if we go up to our graph, let's identify where the inflection points are. So let me write inflection points. Okay, so the only possible inflection points where maybe this thing switches concavity are points like A, B, C, D, and E. But let's just check to see where did it actually switch concavity. Well, it definitely switched at A, because it switched from concave down to concave up. It definitely switched at B, from up to down. It switched at C, from down to up. At D, it didn't switch. It was concave up on both sides. So D is not an inflection point. But E is. At E, it switched from concave up to concave down. And our function was continuous at all of these. I kind of skipped that when I was checking before, but I should. Our function was continuous at all of these, so they are inflection points. So I want to end this video with a theorem, which I'll call the concavity test. This will give us a quick way to check whether functions are concave up or concave down. So it turns out that if our function's second derivative, let me write that better. If f double prime of x is greater than 0, if the second derivative is positive for all x in some interval I, then f is concave up. F is going to be concave up on that interval I. But if the second derivative is less than 0, if it is negative for all values of x in I, then f is concave down. Okay, so to recap quickly, the first derivative tells us about increasing, decreasing. The second derivative tells us about concavity.